Next, we are going to see about semaphore, which is one of the critical section problem. Semaphore is actually a data type, or I can say it as a variable, which is have the access to a common resource by using multiple threads and avoid critical section problems in a concurrent system such as a multitasking operating system. Okay, you are going to use a variable called as s as an integer variable that apart from initialization, and here we are going to use two functions called as wait and signal. If weight of s, if it is less than or equal to 0, we are putting a condition called as busy, which means already the process is in critical section, so it's just need other process have to wait inside the in the ready queue, and we are going to decrement the count. And what is signal function is, the s value will just signal the other processor that the critical section is free. The process which is ready in the ready queue can enter into the critical section. So what is the usage of semaphore here? We have two things here. One is counting and binary semaphores. Binary semaphore, which we already know, which uses zeros and ones. The value of the counting semaphore can range over an unrestricted domain. So thus binary semaphores have behaved similarly to mutex locks here. And counting semaphore, I already told, if a process, each process which wishes to use a resource have to perform a wait operation on the semaphore, and when the previous process release the resource, it performs a signal operation that is incrementing the count. When the count for semaphore goes to 0, all resources are being used. It's the meaning. After that processes that wish to use a resource will block until the count becomes greater than 0. So here is the synchronization problem in semaphore. You have S1 as well as S2, and you have P1 as well as P2. P1 is going to insert statements here. So the order here is, because if the synchronization is initialized to 0, the P2 will execute S2 only after P1 has invoked the signal, which is after statement S1 has been executed. Semaphore implementation. Here we are going to use a structure variable, and you are going to use a pointer list here. So the same case, if you have to wait inside the critical section, it has to be in the value should be decremented. And if you are using release, if the current running process which has completed his work and he or she want to release the thing, it can be counted as value plus plus. So this is signal operation. And block operation will suspend the process that invokes it and wake up, which resumes the execution of a block process. Next comes the deadlocks and starvation. The implementation of a semaphore with the waiting queue may result in a situation where two or more processes are waiting indefinitely for an event. That is called as what? Deadlocked. So here you take the example as P0 and P1 are two processes which are going to have two semaphores as S and Q. P0 is having wait of S and wait has the resource wait of S, and P1 is having the resource called as wait of Q. Now P0 is requesting for wait of Q and P1 is requesting for wait of S. So what happening? No two processes completed their execution, so this situation is called as deadlock. What is starvation? Another problem which is related to deadlock is starvation. By the meaning itself, I can say When a higher priority process is inside the CPU for a long time, other process need to wait, or other process need to starve for a long period. So that is called as what? Starvation. So next topic we will see in the next video. Thank you.